Imagine dropping a marble into a glass of water. It plunges quickly, right? Now picture dropping that same marble into a jar of honey. Notice how it descends slowly, almost reluctantly. This difference in their descent tells a story about a fascinating property called viscosity. Viscosity is the resistance of a fluid to flow. The thicker the fluid, the higher its viscosity, and the slower an object will move through it. Think about ketchup. It's much more viscous than water. That's why we give the bottle a good shake to get it moving. Understanding viscosity is key to understanding how fluids behave. It explains why honey drips slowly, why motor oil protects engine parts, and even why some volcanic lava flows like sticky rivers of molten rock. In the mid-19th century, a physicist named George Gabriel Stokes cracked the code of viscous forces. He formulated Stokes' law, a mathematical equation that describes the force of drag experienced by a small sphere moving through a viscous fluid. Imagine our marble again, sinking through honey. As it moves, it encounters resistance from the honey, a force we call drag. Stokes' law tells us that this drag force depends on several factors: the viscosity of the fluid, the size of the sphere, and the speed at which it travels. The more viscous the fluid or the larger the sphere, the greater the drag force. Similarly, the faster the sphere moves, the more resistance it encounters. Ready to unveil the secrets of viscosity yourself? Let's conduct a simple experiment. You'll need a tall, clear container. A graduated cylinder works best. A stopwatch, a ruler, different liquids like water, oil, and honey, and small spheres of varying sizes, marbles, ball bearings, etc. First, measure the diameter of your sphere and the height of your liquid column. Next, drop the sphere into the liquid and time how long it takes to fall a specific distance. Repeat this process with different spheres and liquids, recording your observations. Using Stokes' law, you can calculate the viscosity of each liquid based on the sphere's size, its terminal velocity, the constant speed it reaches while falling, and the known density of the sphere and the liquid. Stokes' law isn't just a scientific curiosity confined to labs. It has real-world applications that impact our daily lives. Engineers use it to design everything from tiny medical devices like microfluidic chips, which manipulate minuscule amounts of fluids, to massive structures like oil pipelines, where understanding the flow of crude oil is crucial. In medicine, Stokes' law helps us understand how blood cells flow through our veins and capillaries. It even plays a role in the mesmerizing dance of the blobs in a lava lamp, where the changing temperature affects the density and viscosity of the blobs, causing them to rise and fall. From the mundane to the extraordinary, Stokes' law helps us appreciate the fascinating world of fluid dynamics and its impact on our lives.